Now let's try a trickier situation. Instead of friction for an object sliding across a horizontal plane, like just a car on a flat level road, let's instead talk about a block sliding down an inclined plane. This is where, for example, I gradually increase the angle and we see where the block starts to slide down the plane. So a tricky thing about this case is that now in order to figure out what the normal force is, we need to decompose gravity into components that are parallel and perpendicular to the incline itself. So let's start. We want to draw the forces acting on this block. So we'll start out by drawing the gravity vector. So the gravity vector is straight downward. So there is the gravitational force exerted by Earth on the block, and it is just mg. Now this next step is going to be tricky. We want to decompose the gravity vector into components parallel and perpendicular to the surface. So here is a component perpendicular to the surface. And then here is a component parallel to the surface. And you can see if we were to repeat this component down here, then it would add up to this original gravity vector. So this is F gravitational Earth on the block, the parallel to the surface part. And this is F gravitational Earth on the block, the perpendicular part, and then we're going to cross out the original gravity vector. So that's pretty tricky, but you see, if you took this orange arrow and you added this orange arrow to it, you would get the original magenta arrow. So we've decomposed gravity into a component that points downhill and a component that points perpendicular to the surface of the hill. The next thing we want to do is to add the normal force, okay? So the contact force exerted by the surface on the block. So now this is interesting. This only has to oppose the portion of gravity that points perpendicular to the plane. You see? So that's kind of interesting. So this is the normal force by the surface on the block, and it has to be the same magnitude as this perpendicular component of gravity. And that's because there's not going to be any acceleration perpendicular to the surface. You don't have the block jumping up and down on the surface. So the next step is to add friction. Now, before we can add friction, we need to know what kind of friction it is, and we need to know what kind of motion it is opposing. So we were told at the beginning that we're sliding down an inclined plane. So I guess we know that somehow we know that the velocity points downhill. So if the velocity points downhill, then one way or another, friction must point uphill. But we don't know whether it's, well, no, and that's also, we know that it's sliding. Okay, so since we know that it's sliding, it must be kinetic friction. It's not static friction because the block is sliding down the hill, so there is some motion to oppose. So it's kinetic friction, it's going to point uphill, so we know what direction it points. And therefore, I guess we know how big it is, because we always know how big kinetic friction is once we know the coefficient of friction and we know the normal force. So actually, we can draw in the friction arrow right away. We can say, okay, there is F kinetic, and that's going to equal mu kinetic times F normal. There it is on our pre-drawn diagram. The block shown in this free body diagram is it at rest? Is it sliding downhill at constant speed? Is it sliding downhill and speeding up? Is it sliding downhill and slowing down? Is it sliding uphill and speeding up? Is it sliding uphill and slowing down? Well, since friction points uphill, I think it can't be sliding uphill. It must be sliding downhill because, you know, friction would oppose the motion of the block on the surface. So since friction points uphill, it must not be sliding uphill. If now, is it, also we know that it's kinetic, well we wrote down Fk, it's kinetic friction. So I guess if it's kinetic friction, then it must be sliding downhill because there must be motion if it's kinetic friction. So the velocity vector seems to point downhill. And yet, if you look at the balance of forces, the acceleration seems to be downhill because the acceleration vector seems to point downhill because we have the downhill component of gravity is bigger in magnitude than the kinetic friction, which points uphill. So I would say it's moving downhill and it's speeding up since its acceleration points downhill and its velocity also, its velocity also evidently points downhill since the way you infer that the velocity must point downhill is that friction is pointing uphill and friction is kinetic. So I guess it must be opposing some non-zero velocity, which must be downhill in the opposite direction of friction. I think I like C, Charlie, sliding downhill and speeding up. How would I change this free body diagram if the block were at rest? Well, if the block were at rest, then its acceleration would be 0. That would mean that the friction arrow would have to be exactly long enough to offset the downhill component of gravity. And also, if it were at rest, then this friction would not be kinetic friction, it would be static friction. And if it is static friction, we don't know how big it is until we know how big it has to be. So this is F static. And actually, we do know how big it has to be. So in this case, F static must equal this gravitational force, the downhill component. And somehow that must be less than or equal to mu static F normal. So for acceleration to be 0, so if the block is at rest, then it must be static friction rather than kinetic friction, and the acceleration must be 0. And if the acceleration is 0, then these arrows must be the same length as one another. How would I change this free body diagram if the block were sliding downhill at constant speed? Well, there would still be an acceleration of 0 if it's sliding downhill at constant speed. But now, instead of this being static friction, this would have to be kinetic friction. I think otherwise it's the same. So if it's sliding downhill, then it's kinetic rather than static friction. But if the velocity points downhill, then friction must point uphill. So I think that makes sense. So I would just change the static to a kinetic, and I think then it's fine. This is constant velocity, and it's moving downhill. What if the block were sliding downhill and slowing down? Well, if the velocity points this way and it's slowing down, then the acceleration must point this way. In that case, the kinetic friction arrow must be longer than the downhill component of gravity. So we have to make this arrow longer, and then it's no longer the same length as the gravity arrow, so we have to get rid of these hash marks. So we had to make the kinetic friction arrow longer than the downhill component of gravity. In fact, maybe I should exaggerate that even a little more. So now I think it's convincing that it is sliding downhill and slowing down because the velocity is downhill, kinetic friction is uphill, and the acceleration is uphill. So it's slowing down. How would we change this free body diagram if the block were sliding uphill and slowing down? Well, we actually don't need any friction at all to make it slow down if it's sliding uphill. But let's just suppose we have the same friction coefficient as we had before. So in that case, friction, kinetic friction, must point downhill. So the acceleration, I guess if it's sliding uphill and slowing down, then the acceleration points downhill, but the velocity points uphill. So it's sliding uphill. So since it's sliding uphill, we have kinetic friction pointing downhill. but the acceleration is, so it's moving uphill, but the acceleration is downhill. So that means it's slowing down. It's sliding uphill and slowing down. I think that makes sense. So kinetic friction would now point downhill instead of uphill. Here's an old chapter 10 reading question. You've slammed on the brakes and your car is skidding to a stop on a steep and slippery winter road. Skidding to a stop sounds like kinetic friction. Other things being equal, will the car come to rest more quickly if it is traveling uphill or if it is traveling downhill? Why? Consider a free body diagram for each case. Well, we can kind of model our free body diagram off of this previous case we had from a moment ago. So if we are skidding to a stop, I guess that means we're slowing down. If we're slowing down, then our acceleration vector and our velocity vector must point in opposite directions, or at least somewhat opposite directions. And if we're on a hill, we're moving either uphill or downhill, then if we're moving downhill, the velocity vector points downhill and the acceleration vector points uphill if we're slowing down. And if we're moving uphill and we're slowing down, then the velocity vector points uphill and the acceleration vector points downhill. We draw this same diagram, except we'll think about what happens to friction. So we decomposed gravity into the component that points downhill and the component which is perpendicular to the road surface. So it's the same decomposition we did there, I just didn't draw it. And then the normal force balances this perpendicular component of gravity. So the same thing, so this arrow, this arrow, this arrow, this arrow, they're all the same length as one another. It's the same scenario as we have up there. But here we are sliding downhill and we're slowing down. So sliding downhill, then it must be kinetic friction, and the kinetic friction must point uphill. And if I'm slowing down, then it must be enough kinetic friction to be a larger kinetic friction arrow than this downhill component of gravity. So this green arrow must be bigger than this orange arrow. Now, other things being equal, but now instead I'm moving uphill. Well, I'm screeching to a stop, I'm moving uphill and I'm slowing down. Well, gravity points the same way as it did before, but since I'm moving uphill, now friction points downhill. And other things being equal, it must be the same size friction arrow. It just points the other way because instead of traveling downhill, now I'm traveling uphill. So this green arrow just reversed itself because it's going to oppose my uphill velocity, whereas this one was opposing my downhill velocity. So now you say, in which case do I screech to a stop more quickly? Well, here I have two downhill arrows helping one another. Here I have an uphill arrow and a downhill arrow, and they're somewhat opposing each other. The green arrow, the friction arrow, wins, but it's being hindered rather than helped by gravity. Here the green arrow for friction is being helped by gravity. So if I'm skidding to a stop while going uphill, gravity is also helping me to stop, as well as friction helping me to stop. Whereas if I'm skidding to a stop downhill, gravity is making it more difficult for friction to stop me. So I think it's going to take me longer, all things being equal, to skid to a stop downhill than it will to skid to a stop uphill. An object O of mass m slides down an inclined surface S at constant velocity. What is the magnitude of the kinetic frictional force, F kinetic, exerted by the surface on the object? So now we have to start to quantify things. You know that this kinetic friction force by the surface on the object, for the object to be moving at constant speed, then its acceleration is 0. The way I've drawn it here, its velocity is downhill. Of course, it's mirrored over here. So here, its velocity points that way, and in any case, its acceleration is 0. So you see, this is the gravity vector, but it has not yet been decomposed. So then if we decompose that gravity vector, we cross it off, and we draw a component. This is the gravitational vector by Earth on the object, the perpendicular part. And then this is the gravitational force by Earth on the object, the parallel part. And this arrow will be the same length as this arrow, even though I didn't draw it very well that way. And if it's moving at constant velocity, then this arrow will be the same length as this arrow. So we actually know that F kinetic by the surface on the object must be the same as the gravitational force by Earth on the object, the downhill component. Now, how big is that downhill component? Well, if we look a little bit more closely at this diagram, then this angle turns out to be theta. So this angle also turns out to be theta. And then the downhill component that we want here is this yellow arrow. And over here, the downhill component that we want is this yellow arrow. So this is F gravitational, Earth on the object, the parallel component. And this is the analogous thing over here. This is F gravitational, Earth on the object, the parallel component. And you can notice that F gravitational, Earth on the object, the parallel component, divided by F gravitational, Earth on the object. So that is opposite over hypotenuse. So that is sine theta. So in fact, this equals mg sine theta. Oh, this equals mg sine theta. Okay, so we have F gravitational, Earth on the object, the downhill component. The downhill component of Earth's gravitational force on the object is mg sine theta, and that's going to equal the force of kinetic friction by the surface on the object if we are at constant velocity. So, and that is going to equal, mg sine theta, so I think I like answer B. Bravo. There actually is one other answer that turns out to be correct, but we have to do more steps to get to it. Same scenario. What is the magnitude of the gravitational force exerted by Earth on the object? Well, I think it's just mg. What is the magnitude of the downhill, that means tangential or parallel component, of the gravitational force exerted by Earth on the object? So that's basically asking about this thing, the parallel component of the gravitational force by Earth on the object, and it is mg sine theta. And again, the way that we saw that is we decomposed mg into a component perpendicular to the surface and a component parallel to the surface. And if you take this arrow and redraw a copy of it down here, you can see that this is opposite over hypotenuse is this length divided by mg. So this must be mg times sine theta. Same scenario, what is the magnitude of the normal force exerted by the surface on the object? The normal force exerted by the surface on the object will be the same magnitude as the perpendicular component of the gravitational force. On this diagram, that is this orange or salmon colored line here. On this diagram, it is this line. And again, we have this angle theta, so we can say Fg, Earth on the object, the perpendicular component, divided by mg, basically, equals, so this is adjacent over hypotenuse, so this is cosine theta. So therefore, this gravitational force by Earth on the object, the perpendicular component, Oh, and this equals F normal. I mean, it's the same as F normal because they have to balance to keep the object from bouncing up and down in this direction. So this is mg cosine theta. So I think I like this answer, C, Charlie, mg cosine theta. Since the object is sliding down the surface at constant velocity, the forces acting on O must sum vectorially to 0. How do I express this fact for the forces acting along the downhill, that's the parallel or tangential axis? So in that case, you're saying that the uphill frictional force must be the same in magnitude as the downhill component of gravity. So we take this statement and then we can add to it the statement that this equals mu kinetic times F normal, which is an F normal is mg cosine theta. So this is saying, yeah, so you see this is mu kinetic mg cosine theta, and meanwhile we showed a couple pages ago that this equals mg sine theta. So mg sine theta equals mu kinetic mg cosine theta. Oh, let me rewrite that up here. So mg sine theta equals mu kinetic mg cosine theta. And that is expressing the fact that F gravitational in the parallel direction, that's the downhill component of the gravity force, must be the same magnitude as the frictional force because they are balancing each other because the object is moving downhill, sliding downhill at constant velocity. So how do we express that? I think mu mg cosine theta equals mg sine theta. I think I like E, echo here. Mu k mg cosine theta equals mg sine theta. I like that one. Suppose friction holds object O at rest on the surface. Which statement is true? Okay, so now the acceleration is 0, so the forces have to balance. The velocity is 0, so it has to be static friction rather than kinetic friction. Static friction by the surface on the object must be the same magnitude as the gravitational force Earth on the object, the downhill or parallel component. And that's just because you would subtract them to get the mass times the downhill acceleration, but the acceleration is 0, equals mg sine theta. So the downhill component of the gravity force is mg sine theta. We worked that out because it's the same as this yellow arrow, and we had opposite over hypotenuse, that's the sine theta. And then meanwhile, we have F static of the surface on the object must be less than or equal to mu static times F normal, and mu static F normal, that's mu. So F normal we determined earlier was, we have F normal is mg cosine theta because the normal force has to balance this into the plane component of gravity. So this is less than or equal to mu static mg cosine theta. So then I think what that's saying is mg sine theta from up here equals the static friction force, which must be less than or equal to mu static mg cosine theta. And I think that statement is mg sine theta equals F static, which must be less than or equal to mu static mg cosine theta. It has to be S for static. Yeah, so I like this, D, delta. So what that's saying is that if you take this gravity arrow and you cross it out, and then you decompose it into a component into the inclined plane, that's the that's the component that balances the normal force, and then you have this downhill component of gravity. We know that this downhill component of gravity has to be balanced by the static friction force if the object is held in place statically. By the way, it's important to cross off this original gravity arrow when we decompose it so that we don't accidentally count it twice. That's why we crossed it off. We crossed it off so that we remember that we've already, that we've redrawn it and in the form of its components. Suppose friction holds the object at rest on the surface, then I gradually increase theta until the block just begins to slip. Which statement is true at the instant when the block starts slipping? So then this less than or equal for static friction becomes an equal sign. So this becomes an equal sign when we start slipping. So the one with an equal sign, it's this one. B, bravo. mg sine theta equals, okay, this is the downhill component of gravity. So mg sine theta is the downhill component of gravity. That has to be balanced by the static friction force. And the static friction force at the instant when it's just beginning to slip. So it's just about to slip. So it's like just you're just about to make it start slipping. Mu static times F normal. F normal equals mg cosine theta because F normal has to balance this component of gravity, which points opposite F normal. Again, that is the classic situation where we take our object on the plane and we tilt the plane until it just starts slipping. There we go. That's where it just starts slipping, and in fact, if you take this equation with the equal sign, you get that mu static equals tan theta, where the object just starts slipping. Mu static is sine theta divided by cosine theta. Everything else cancels out. So mu static equals tan theta is where the object just starts to slip.
So we can make our icy driveway a little bit more steep, a little bit more steep, a little bit more steep. As we do that, two things happen. One is that this downhill component of gravity gets bigger, and the other is that this into the driveway component of gravity gets smaller. And eventually we start slipping. So this is wood on wood. So this is wood on wood, and I'll lift it up until it just starts to slide down. Okay, and then by contrast, this is sandpaper on wood. So let's try the sandpaper on wood, and I'll lift it up until it just starts to slide down. I hope it's a steeper angle than the wood on wood. I didn't try this in advance. Does seem to be steeper. Oh, there we go.
Remember, the reason why when we do this decomposition we cross off the original gravity arrow is because we don't want to double count gravity. So once we've taken the gravity arrow and decomposed it into two arrows that add up to the original arrow, we want to cross off the original arrow so that we remember we no longer have to count it when we write F equals ma. So normally the way we do that, so here is the original gravity arrow, and then we will cross it off and replace it with, here is the downhill component, and here is the into the plane component. So those are the parallel and perpendicular components of the gravity force. This is the original gravity force. This is F gravity parallel and F gravity perpendicular. Then we know how big to make the normal force. So this is, we usually call this the normal force because it balances this component of gravity which points into the plane. And then what we do with the friction force will depend on the situation. You know, is the friction force holding it in place, preventing it from accelerating? If that's true, then it has to be exactly big enough to offset this downhill component of gravity. So if it's constant, if it's zero velocity, then this arrow is the same size as this arrow, and this is static friction. If it is constant velocity downhill, then this arrow is the same length as this arrow, and it's kinetic friction rather than static friction. I don't think constant velocity uphill is possible. No, constant velocity uphill is not possible without some other external influence. Or it may be that the acceleration is not zero, in which case these don't have to offset each other exactly. Like you could be sliding downhill and slowing down, in which case you'd have this kinetic friction arrow be bigger than this downhill component of gravity. Or you could have sliding downhill speeding up, in which case this kinetic friction arrow would be shorter than this downhill component of gravity, and so on. So there are many possibilities for the friction. Here's a chapter 10 problem that may or may not fit in our worksheets. Coefficient of static friction of tires on ice is about 0.10. Okay, so we have mu static equals 0.10. What is the steepest driveway on which you could park under those circumstances? So maybe you want to answer B first. Draw a free body diagram for the car when it is parked successfully in an icy driveway that is just a tiny bit less steep than this maximum steepness. We might want to do B before A. Huh. So I think we already have that diagram. This is static friction perfectly balancing gravity, and we know that F static is less than or equal to F normal times mu static. But if it's just a tiny bit less, it's like essentially equal to the maximum value, then we're going to say it's basically equal. Well, actually, we don't, just equal. So, you know, we're approaching that limit. So it's equal. It's like equal in that limiting case. We can just look at this and say the acceleration downhill must be zero because it's just barely successfully parked there. So that says that the static force of friction balances this downhill component of gravity. F gravity parallel. And the downhill component of gravity is mg sine theta. And okay, and then meanwhile, this must equal, we said over here, that must equal mu static times the normal force has to equal this mg sine theta. What's the normal force? Well, you see, we're not accelerating in this direction either, so the normal force must balance the into the plane component of gravity, this perpendicular component of gravity, which is, we argued earlier, was mg cosine theta. So this F normal is mg cosine theta. So we have mu static mg cosine theta equals mg sine theta. This is the result we just got a minute ago. You see everything cancels except for, you get mu, well, you get sine theta divided by cosine theta equals mu static. So that's tan theta equals mu static. So then you get theta is arctan of mu static. And then you have to make sure you get degrees versus radians correct. But theta is arctan of 0.1, which is something like 6 degrees. Okay, 5.7 degrees if I do it carefully. That's because a radian is about 57 degrees. Oh, answering part A starts by expressing in math which statement? The total gravitational force, no. The downhill component of the downhill component of gravity equals the largest possible, here we go. Yes, the downhill component of gravity equals the largest possible value of static friction. Exactly. You see, that's what we wrote. The downhill component of gravity has to equal the largest possible value of static friction right at this limiting case. A fried egg of mass m slides at constant speed down a Teflon frying pan tipped at an angle theta above the horizontal. By the way, this only works if the angle theta is just right. Draw the free body diagram for the egg. Well, it so happens that we already have it, except that we have to call this kinetic friction. Okay, what is the vector sum of forces acting on the egg? Well, it must be 0, right? The vector sum of forces acting on the egg is 0. So all the forces acting on the egg balance because the velocity is constant. So the acceleration is 0. So that is the free body diagram. You could then draw some conclusions from this. This kinetic friction force, F kinetic, equals this downhill component of gravity. And F kinetic is mu kinetic F normal. And then this F gravity is mg sine theta. That's the downhill component of gravity. And F normal is actually mg cosine theta. So this is mu kinetic mg cosine theta equals mg sine theta, which then lets you conclude, in this case, that mu kinetic is tan theta. So that's where the statement comes from, that this only works at exactly the right angle. It only works if we are tilting the pan such that the tangent of the angle equals the coefficient, in this case, the coefficient of kinetic friction. How do these answers change if the egg is instead speeding up as it slides? Well, if the egg is speeding up as it slides and it's sliding down, so in this first case we had B was pointing downhill, but we had A equals 0. But now if the egg is speeding up as it slides, it's still moving downhill, but it's accelerating downhill also. So if it's speeding up, then the acceleration tends to point in the same direction as the velocity, or at least they tend to point, at least their dot product is positive. I'll put it in math terms. If it's speeding up, these two vectors are no longer the same length. The friction arrow must be shorter than the downhill component of gravity. So there we go. So if we do this, then now the egg is speeding up because the acceleration is going to point downhill, because this orange downhill component of gravity is bigger in magnitude than this green kinetic friction term. A heavy crate has plastic skid plates beneath it and a tilted handle attached to one side, which requires a smaller force directed along the diagonal rod of the handle to move the box. Why? Is pushing the crate easier than pulling? Or is pulling the crate easier than pushing? Or is there no difference? So the point is that the force used to either push or pull the box is oriented along this axis. So somehow we're either pushing the box downward a little bit, with a little bit of a downward component, so you imagine maybe there's a hinge here. So imagine there's like a hinge, and you could be pushing the box this way with a stick, or you could be kind of pulling it this way with a rope. And the question is, which one makes moving the box easier, or does it not make any difference? And by easier, we actually mean the magnitude of the force that you have to apply to this rod or rope here. So you could think intuitively, here's one way to think about this. When you pull the box, then you are exerting a force that has a component this way, horizontally, but it also has a component this way, vertically. And if that component this way, vertically, is upward, then you are somewhat offsetting the downward gravitational force that the normal force has to balance. So I think you are somewhat going to reduce the friction between the box and the surface, because this slightly upward component of your pull, if you're pulling the box, is going to make the friction correspond to the friction of a slightly lighter, less heavy box. Whereas if you're pushing the box, then there's a slight downward component to your push, and that downward component has to be counteracted by an additional component of the normal force. So I think when you push on the box, then the friction between the box and the floor is going to be equivalent to the friction of a slightly heavier box than this box because of that slight downward component of your push. So I think pushing the box will be more difficult, will require a bigger force than pulling the box. I think pulling the box will require a reduced force. I think pushing the box will require an increased force as compared with just moving it horizontally, although it says compare one with the other. I think pulling is easier than pushing. So I'm going to predict that the answer will be B, but we don't really have, other than our intuition, we don't have a quantitative way to work that out yet. So we're going to go through step by step and do that. But I think pulling will be easier than pushing, because if you take this force and decompose it into components, this horizontal component is going to counteract friction to make the box move. This vertical component essentially is going to reduce the necessary normal force by the floor, so that will tend to reduce friction. Whereas if you push, then there's a downward component, and that downward component is going to increase the necessary normal force between the floor and the box, and that will increase friction.
The force of my push or of my pull is directed along the axis of this rod. So in one case, I'm pushing, and in the other case, I'm pulling. You have to imagine this crate is just a flat surface sliding along a flat floor, and there are no wheels involved.
Here's a problem with the same scenario, except that now you've decided that it's pulling rather than pushing. So a woman applies a constant force to pull a 50-kilogram box across a floor at constant speed. Okay, so across the floor, constant speed. So I think this is going to imply constant velocity, because it's also not changing direction. She applies this force by pulling on a rope that makes an angle of 37 degrees above the horizontal. So there's this angle theta, and that theta will turn out to be 37 degrees. Well, it's given. And the friction coefficient between the box and the floor is mu kinetic is 0.1. Find the tension in the rope. Whoa. How much work does the woman do moving the box 10 meters? Whoa. Okay, so we'll find the tension in the rope. What are all the forces acting on the box? This is very tricky. So let's try it first, and then we'll see what I did on my earlier diagram. So I guess we often start out with gravity. So there is F gravitational by Earth on the box, whose magnitude is mg. And if the box is moving to the right, then there must be a frictional force. Although let's not draw that just yet, because we're going to want to make it match. We're going to want to make it match something else to get constant speed. So let's not worry about that yet. Okay, let's draw here is the tension in the rope. So this is the contact force by the woman on the box, and its magnitude equals the tension in the rope. And then we are going to want to work out how big is this frictional force, and what kind of friction is it? Well, it's sliding across the floor, so this must be kinetic friction. So this is kinetic friction by the floor on the box. Are we missing anything? I think we are missing something. I think we're missing the normal force. So there's also the normal force exerted by the floor on the box. Now, in past problems on a horizontal surface, we just said the normal force equals mg. And then on our inclines, we usually said the normal force is mg cosine theta. But remember, the normal force is whatever is needed to prevent the box from bouncing up and down this way. So we don't know yet what the normal force needs to be. So let's take this tension force and decompose it into horizontal and vertical components. So we're going to draw, this will be the contact force between the woman and the box, the x component. So we'll say x is this way and y is this way. We're going to cross this off, and we'll say this is the contact force between the woman and the box, the y component. And this will equal t, so this is theta, so this will equal t cosine theta, because this is adjacent over hypotenuse. And this will equal t sine theta, because if you were to take a copy of this vector and draw it over here on the right side, then you would get opposite over hypotenuse. So you take this vertical component of the tension, and that divided by the whole tension is opposite over hypotenuse, which is sine of theta. So this vertical component is t sine theta. And we know the acceleration is 0, so we know that 0 equals m a sub y, which is, so we have the normal force is upwards. We'll do up minus down. So this is the normal force plus t sine theta. Those are both up. And then minus down, which is mg. That's one equation. And then we have the forces in the x direction. So it's not accelerating. So 0 is ma in the x direction. So we have right minus left. So this is t cosine theta minus F kinetic. Oh, and by the way, what is F kinetic? F kinetic should equal mu kinetic times F normal. So this should be mu kinetic times F normal, which equals t cosine theta minus mu kinetic F normal. Okay, so that equals 0. I think the free body diagram we just drew is the same as the free body diagram that I drew in the distant past. If T is the tension in the rope, then what is the normal force by the floor on the box? Well, I think the normal force plus T sine theta has to equal mg. So I guess if you were going to answer this, I would say that F normal plus T sine theta equals mg, because the two up things together have to balance the one down thing. So I guess that would give me F normal is mg minus T sine theta. So I think I like this one. See, because that gives me F normal is mg minus T sine theta. The way I would get that is not so much to write it directly, but to say that there's no acceleration in the vertical direction, so acceleration is 0. So the vector sum of forces in the y direction is 0. So that's up minus down. So that's normal force plus T sine theta and then minus mg. Okay, so I like this. I like E, echo. F normal is mg minus T sine theta. We might even want to write that down. By the way, I said a couple of pages ago that pulling the box reduces the normal force. So you see, pulling the box reduces the normal force. Step 2, what is the frictional force exerted by the floor on the box? Well, it must be F normal times mu kinetic. F kinetic is mu kinetic times F normal. So that must be that F kinetic is mu kinetic times this expression we had before, mg minus T sine theta. Ooh, I think I like this, A alpha. So F kinetic is mu kinetic times mg minus T sine theta. Step 3, how do I use the fact that the box is moving at constant velocity and hence is not accelerating? So we already used the fact that the box is not accelerating vertically to balance the gravitational force with the combination of the normal force and the vertical component of the tension. But now we can use the fact that the forces balance horizontally, there's 0 acceleration horizontally, to say that this kinetic friction force has to balance the horizontal component of the tension. So I think, well, actually we have it here. See? T cosine theta minus mu kinetic F normal equals 0. T cosine theta, which is the horizontal component of the tension, has to equal the force of kinetic friction, which we wrote down up here. So that is mu kinetic mg minus T sine theta. So I think it seems to be this one, B, bravo. So the horizontal component of the tension has to balance the friction force, which is mu kinetic times mg minus T sine theta. So if we solve this for the tension, we get this expression which matches what I wrote on the slide. And sometimes if you get an expression like this, it's worth thinking about limiting cases. If theta is 0, that means she's pulling horizontally. If she's pulling horizontally, then cosine theta is 1 and sine theta is 0, and you get mu k mg. And that makes sense because the tension in the rope just has to match friction, and friction would just be the normal force, which would just be mg times the coefficient of friction. So this result, if you plug in theta equals 0, is just what you would get if you were pulling a box not at an angle at all. So it's just mg times the coefficient of friction. And then you could even try plugging in theta is 90 degrees. If theta is 90 degrees, cosine theta is 0, sine theta is 1, and the mu cancels out, and you get the tension is mg. Even that makes sense because you're just holding the whole box. So you're basically holding the box's weight with the rope. So I guess those two limiting cases make sense. So if we plug in numbers, we get that the tension is 57 newtons. So I guess we got the tension. Now the tricky part is we're going to say how much work does she do moving the box 10 meters. And the tricky thing about this is that the work is the force dot product with the displacement. I guess we could say delta r, but the displacement. So if they're in the same direction, then you just multiply them. But if they're not in the same direction, then you have to say that's the force times the displacement times the cosine of the angle between the force and the displacement. And in this case, the force is in this direction. It's a little bit upward, and the displacement is horizontal. So we actually want the component of the force which is in the same direction as the displacement. The component of the force which is in the same direction as the displacement is t times cosine theta. The work is t cosine theta times delta x. So that's going to be 57 newtons times cosine theta. So cosine theta turns out to be 0.8, and then times 10 meters. This is the cosine theta factor. So in part A, we found the tension in the rope is 57 newtons and is oriented at an angle of 37 degrees above the horizontal. In 2 dimensions, work is displacement times the component of the force along the direction of the displacement. In this case, the displacement is horizontal, so we want the horizontal component of the force. So the work done by the rope on the box is the dot product of the force with the displacement, dot product or scalar product. But basically, right, it's the dot product of the force exerted by the rope on the box with the displacement of the point of application of the force. But the easier way to see this is the displacement is entirely horizontal. So we only want the horizontal part of the force to get the work. So we take the horizontal part of the force times the displacement, which is horizontal. If we had both horizontal and vertical components, we could say the work is the horizontal component of the force times the displacement in x plus the vertical component of the force times the displacement in y. That's what this scalar product, the dot product, means. But we only displace the box in x. We don't displace the box in y. So we only want the horizontal component of the force times the displacement, which is horizontal. So that's what we did here. We said tension times cosine theta times delta x. Delta x we're given is 10 meters. The tension we solved for is 57 newtons. And then the cosine of 37 degrees turns out to be 4/5, which is 0.8. So I get a work value of 456 joules. So I think I like answer B here. 10 meters times t cosine theta, which is 10 meters times 57 newtons times 0.8. So that is 456 joules. I think I like B. Bravo in this case. So that's pretty tricky, right? This is a pretty tricky problem. Now if we return to this conceptual question, is it easier to push or to pull? Well, it turns out if we were pushing, then we would get a plus sign here, and we get a plus sign here. So pushing would mean that the force that we apply adds to the required normal force, which then adds to the frictional force, which then adds to how big a force we have to use to move the box. Because we were pulling, the friction was actually smaller than mg times mu, right? So the friction force, instead of being mu times mg, the friction force was mu times mg minus the vertical part of the tension. That's because we were pulling. If we'd been pushing instead of pulling, then the normal force would have been bigger than mg instead of being smaller than mg. And that would in turn make the friction force bigger, which would in turn make the force that we have to apply to move the box bigger. So I claim that pulling the crate is easier than pushing. I guess we didn't go all the way through proving that because we didn't work through the result for the pushing case. But basically, if we were going to work through the result for the pushing case, we would find that this minus sign becomes a plus sign because the vertical component of the pushing force then increases the required normal force to make the forces balance in the vertical component. That was a huge amount of material, so you will certainly be ready for fall break after all of this. And I'm sure we will not work through 100% of this before fall break. We'll do projectile motion and we'll do some of the easier friction problems, and then we'll probably do some of the trickier friction problems just after fall break.